Hello, I'm going to talk about my recent paper, Beating Two-Thirds for Random Order Streaming Matching. I'm Soheil Behnezhad, and this is a joint work with Sepehr Assadi. So we studied the maximum matching problem, and as a quick reminder, recall that a matching in a graph is a set of edges, the red edges here, such that they do not share any vertex, right? So they are essentially vertex disjoint. And the maximum matching problem is to find a matching of maximum possible size. We study this problem particularly in the streaming setting, or more specifically, the graph streaming setting. Here, the edges of the graph arrive one by one in a stream. And the goal is to have just one single pass over this input and output the property of the graph, here, a maximum matching of the graph using a small space. And how much space do we allow? Well, we are particularly interested in the setting where for n vertex graphs, we require near linear in n space, particularly n polylog n space. And note that this is near optimal because the output, which is a matching, can be as large as linear in n. And the setting, particularly with n polylog n space, has been studied for various graph problems, is a standard model, and is called the semi-streaming setting in particular. So trivially, as the edges of the graph arrive one by one, we can construct a greedy matching, particularly every edge that arrives, we add it to the matching if we can. And at the end, what we get is what is called a maximal matching, a matching that we cannot directly add any edge to it. And the maximal matching is known to be at least half the size of a maximal matching. So we trivially get a half approximation using only O of n space. And not particularly that the maximal matching is not may not be larger than half the size of a maximum matching. And here's an example. Particularly if the middle edge arrives first, we add it to the matching. We are not able to add the other two to the matching, whereas the maximum matching size here is 2. And interestingly, this simple half approximate algorithm remains the best known algorithm in the semi-streaming setting. In particular, it's a big open problem to determine whether there is an algorithm with a strictly better than half approximation using a polylog space. On the lower bound side, we know that any better than 0.59 approximation, any larger approximation larger than 0.59, requires more than n polylog n space, much more than n polylog space. This is a recent result of Caprala from Soto 21. But note that there's still a relatively big gap between half approximation and 0.59 approximation. And this is one of the big mysteries of the streaming graph algorithms. Note in particular that this streaming setting is in some sense doubly worst case, right? So the input graph itself is adversarially picked, and the arrival order of the edges is also adversarially picked. There's another natural model where the graph is still picked adversarially, but the edges are processed in a random order. Particularly, the arrival order is a random permutation of the edge set of this graph that's picked adversarially. And this is called the random order streaming setting. And this is what we will particularly focus on today, and study the same maximum matching problem. Good. So the first natural question is, can we beat this greedy half approximation in the random order streaming setting? And the first barrier is that the greedy algorithm, the greedy maximal matching algorithm, is still only half approximate. And this is an example shown first by Dyer and Fries. On the left-hand side, we have a maximum matching of this graph. And on the right-hand side is what a typical maximal matching that's obtained by processing the edges in a random order looks like. Right? So in particular, most of the edges will be picked from the dense middle part of the graph, leaving most of the verses outside unmatched. So it's not going to be better than half approximation. But the good news is that due to a breakthrough of Conrad, McNeas, and Matthew from 2012, we have better algorithms in the random order streaming setting. And this is a table of known results prior to our work. Particularly, there are 2 lines of works. One is based on length 3 augmenting paths. These algorithms start with a half approximate matching and try to find length 3 augmenting paths, applying which give better than half approximation. Particularly, the best known approximation ratio within this framework is the 0.6 approximation of Farhadi et al. For bipartite graphs and 0.54 for general graphs. On the other hand, there's another line of work based on the notion of edge degree constraint subgraphs, or EDCS, which was introduced first by Bernstein and Stein in the context of dynamic algorithms. But for the random order streaming setting, EDCS can be used to get a near 2/3 approximation, which is around 0.66, using the original paper of Assadi et al. Gave n root n space, not really in the semi-streaming setting, but then Bernstein gave an elegant proof reducing the space to linear in n. So prior to our work, the best known algorithm was this algorithm of Bernstein, 2/3 approximation and log n space. And the algorithm of Bernstein actually matches a natural barrier for the problem. First, for the first line of work on discovering length 3 augmenting paths, even if we discover all length 3 augmenting paths, the resulting matching is not going to be necessarily better than 2/3. So there are examples leaving no length 3 augmenting paths where the matching is only 2/3 approximate. And on the other hand, for the second line of work based on EDCS also, 2/3 is a barrier. So there are examples where if you find an EDCS of that graph, it only involves a 2/3 approximation. But more interestingly, this 2/3 approximation turns out to be the right answer for several related models. In particularly in the one-way communication complexity of matching model, and in the fault-tolerant matching model. And I'm not going to define these models because they're not needed for our talk. In both of these models, an EDCS can be used to obtain a 2/3 approximation, similar to the streaming setting, the random order streaming setting. But for these models, it can be proven that better than 2/3 approximation is impossible. In other words, EDCS obtains the best possible bound. Question is this 2/3 approximation also the best possible for the random order streaming setting? In particular, Bernstein asked whether it's possible to go beyond 2/3 approximation in the random order streaming setting. And this is the problem that we answer in this work. And as the title of the work suggests, we show that in fact, it is possible to go beyond 2/3. And so we separate the random order streaming setting from these two other models and show that here, better than 2/3 approximation is actually possible. A result particularly is we show that a 2/3 plus some small constant approximation is possible using n log n space. And in terms of the techniques, we, in a sense, unify these two mostly disjoint lines of work. Our approach is heavily dependent on the EDCS idea, and we also apply a small length 5 augmenting paths. Good. So because our algorithm builds on the prior works heavily, I first have to quickly overview the prior works and then get to our actual contribution. So let me quickly overview what the first line of work based on augmenting paths does. So the intuition of the Conrad, McNeas, and Matthew, who first gave a better than half approximation in the random order streaming setting, was the fact that they started with this greedy maximum matching algorithm processing the edges in a random order. And they showed that either this algorithm obtains a strictly better than half approximation, or a near half approximation is constructed very early on in the stream. Right? So particularly if you recall the example where a randomized order greedy maximal matching is not better than half approximation, note that this middle part is really dense. So even if you see a tiny fraction of the edges in the stream, you do construct the half approximation early. And then what they do is they first construct this half approximation early on, and then use the rest of the edges of the stream finding length 3 augmenting paths. So this was the overview of the work of Conrad, McNeas, and Matthew. But the other works in this augmenting path-based line of algorithms in the literature all follow the same approach. The differences are in how efficiently you can find like length 3 augmenting paths and how many of those length 3 augmenting paths that exist you discover. The second line of work, on the other hand, is based on a completely different idea. It's an edge degree constraint subgraph, and an EDCS, which, as I said, was first introduced in the context of dynamic algorithms by Bernstein and Stein, is a sparse subgraph of the original graph, G, satisfying some degree constraints. I'll actually talk in more details about EDCS as we go forward. And it's guaranteed that if you construct this edge degree constraint subgraph, this graph is sparse and includes a 2/3 approximation of the maximum matching of the original graph G. The challenge, however, is constructing an EDCS. In particular, the first work of Assadi et al. Showed that if we allow n root n space, we can construct an EDCS under random arrival of the edges. And then later, Bernstein gave another construction with n log n space with a relaxation. Good. And both works do require random arrival of the edges in a crucial way. Good. So now let me talk about our algorithm's outline. So particularly, the first step of our algorithm or our analysis is to show that for any input graph G, either the algorithm of Bernstein, the 2/3 approximate algorithm of Bernstein, is actually strictly better than 2/3 approximate. Or if it's not strictly better than 2/3 approximate, and there are examples where it's not better than 2/3 approximate, in all these examples, a close to 2/3 approximation is obtained after merely observing little O fraction of the edges of the string. So this 2/3 approximation is obtained very early on in the string. And then in the second case, if the algorithm of Bernstein does not find a strictly better than 2/3 approximation, we now have all the remaining edges of the stream, and all we have to do is to discover a number of small augmenting paths. Particularly, we find a number of augmenting paths of length up to 5, and it's necessary to go actually beyond length 3 augmenting paths. I'll talk about this as well. Good. So to actually compare this outline with the framework of Conrad et al., recall that they first obtain a half approximation by giving a better analysis of the randomized greedy maximal matching algorithm, and then spend the rest of the stream finding length 3 augmenting paths. Here, we're following very much the same idea, in the sense that we also show that if the algorithm of Bernstein is not now better than 2/3 approximation, we find this 2/3 approximation very early on, and then spend the rest of the stream augmenting this early 2/3 approximate matching. But however, the details are very different. We're dealing with EDCS, and in fact, we prove a deterministic property of EDCS, whereas the proof of Conrad et al. Was based on random arrival of this. So the randomized part of the greedy matching algorithm is very important. And also, of course, like we go beyond length 3 augmenting paths in the second case. Good. So now let me tell you a little bit about the first step, and then I'll talk about the second step. So for the first step, I'll first need to give some more background on EDCS, what it is exactly, and why it is 2/3. So the definition of EDCS is as follows. We are given a graph. We would like to pick a subgraph H of this graph, right? So particularly the vertex set is the same in H and G, and H only includes some of the edges of G. So it's an edge subgraph satisfying these two main constraints. And an EDCS also has a parameter beta, right? So think of beta for the purpose of this talk as some large constant. Right. So a subgraph H of G is a beta EDCS if it satisfies the following two constraints. First constraint says that for any edge inside H, let's take, for example, this edge, the degree of its endpoints in H should be bounded by beta, should be at most beta. And note that particularly I'm talking about the degrees in H, and in fact, throughout the talk, I'll never talk about the degrees in the original graph. I'll always talk about the degrees in the subgraph, in the EDCS. So the first property says that any edge included in the EDCS should have edge degree bounded by beta, and edge degree is sum of the degrees of the endpoints of the edge. On the other hand, the second property says that if you're missing an edge, if an edge is missing from H, but it exists in G, then the edge degree of that edge should be at least beta minus 1. So in other words, in some sense, the EDCS that we have picked, the subgraph that we have picked, should somewhat cover this edge. So the degrees of the endpoints of this edge should be large, sum of degrees. So this is the definition of EDCS. And some basic properties of EDCS are that because the edge degrees are bounded by beta, vertex degrees are also bounded by beta. And so the graph has at most n beta edges. Beta is the constant, so the graph is only going to include O of n edges. And the second property is that an EDCS for any beta at least 2 exists. So any graph G for any parameter beta larger than or equal to 2 has a beta EDCS. There's a constructive proof. The proof it greedily, iteratively picks an edge violating one of the 2 properties and fixes it. The proof, however, is a little challenging because once you fix an edge, it may lead to new violations. But the proof shows that this process eventually terminates, and at the end, we have a valid EDCS. And particularly because of the same challenge, this construction is not directly implementable in the streaming setting. You may have to fix an edge multiple times, but in the stream, an edge arrives only once, and you have to decide whether you want to keep it in your memory. So the constructions are very different from this greedy construction. Good, and the main property of EDCS is that so long as this parameter beta is larger than some constant, we get arbitrarily close to 2/3 approximation. And here, throughout the talk, I will use mu to denote the size of maximum matching. Right? So if beta is larger than 1/epsilon², we get that the mu of h is at least 2/3 minus epsilon mu of g. Good, and this is actually tight, and in a very strong sense. Even if we allow beta to be all the way up to linear in n, know that our EDCS now has n beta, which is n² edges. Even if we allow up to n/3 beta, EDCS may not have larger than 2/3 size the maximum matching of the graph. And here's an example. The red edges form a perfect matching in the graph. And these blue edges can be confirmed to be a valid EDCS of this graph. In particular, all these edges are missing from the EDCS. And one can confirm that these blue edges only include a 2/3 approximation of the perfect matching. All right. So now let me tell you about our first contribution. We give a characterization of these tied instances of EDCS. We show that this is not just one example where EDCS fails to go beyond 2/3 approximation, but that in fact, every instance where EDCS obtains only a 2/3 approximation looks very similar to this. Formally, we show that either the EDCS H includes a strictly greater than 2/3 approximation, or there's a missing matching M of size at least 1/3 of the maximum matching G, such that its endpoints are connected to 2 vertex disjoint blocks with degree close, near regular blocks with degree very close to beta/2, right? So all the vertices here have degree very close to beta/2. All the vertices here also have degree very close to beta/2. Same for these vertices and these vertices. And these blocks are vertex disjoint. All right. Unfortunately, for the interest of time, I won't be able to give the proof of this characterization. However, if you're interested, you can look at a longer version of this talk in the following link. Now, what I will show is how we can prove the guarantee of the first step using this characterization. Recall that our lemma is to show that our lemma states that either the algorithm of Bernstein already obtains a strictly greater than 2/3 approximation, or it obtains a close to 2/3 approximation very early on. All right. Actually, all we need from the algorithm of Bernstein is the following property. The algorithm of Bernstein implicitly constructs an EDCS H consisting of 2 types of edges, edges H early and edges H late. And H is a union of these 2 types of edges. Particularly, every edge in H early arrives very early in the stream, within the first legal O1 fraction of the stream. The edges of H late come later, but H late is just one matching of the graph. In particular, H late has maximum degree 1. Good, so this is all we need from the algorithm of Bernstein. And this is how we can prove the lemma. For proving lemma, it suffices to show that either mu h is at least 2/3 plus some constant times mu g, or mu of h early is nearly 2/3 of mu g. So suppose that the first does not hold, we prove the second. Meaning that suppose that mu h is not strictly better than 2/3 approximation, meaning that the EDCS is not strictly better than 2/3 approximate. We prove that h early itself includes a nearly 2/3 approximate subgraph. Good. So by our characterization of how tight instances of EDCS where h does not include a strictly better than 2/3 approximation look, we know that there's a missing matching M connected to disjoint blocks looking like a regular graph of degree beta over 2. Now, suppose that like all the blue edges here are from the whole subgraph H, but now suppose that we remove all the edges of H late from it. Because H late is just one matching, because its maximum degree is 1, it doesn't change the degree of the vertices by much. The remaining blue edges that are all from H early still look very much like a regular graph. And so we can find near perfect matchings matching all the vertices of M. And because these blocks are vertex disjoint, the size of this these two matchings combined is twice the size of M. And because M itself had size at least 1/3 of maximum matching of G, this perfect matching that now near perfect matching that we constructed for the endpoints of M has size at least 2/3 G, and all of the edges come from H early. Now, let me also talk a little bit about the second step. Now, what do we know? We know that either algorithm of Bernstein obtains a strictly better than 2/3 approximation. In that case, we get what we want. Or just looking at the first little O1 fraction of the edges, we can construct a 2/3 approximation of the maximum matching of the graph. We have a matching M of size at least 2/3 approximation of the maximum matching of the graph. All we have to do is to find augmenting paths in the rest of the stream to go beyond 2/3 approximation. And as what works in the first line that I highlighted, we use augmenting paths. In particular, what is an augmenting path? It's a path that alternates between matching edges and non-matching edges. Here, particularly the red edges form the 2/3 approximate matching that we have, and the blue edges are edges that are not in this matching. And if the first and the last edge of the path are not part of the matching, we can swap them, include them in the matching, throw out the edges inside, and we will get a larger matching at the end. Okay. So we would like to discover these augmenting paths. And the first observation is that to go beyond 2/3 approximation, we do need to go beyond length 3 augmenting paths, but particularly we have to consider length 5 augmenting paths. And this is one example why. Here, the red edges form a 2/3 approximation of the matching. And any path that you consider in this graph has length at least 5. Good. And the main difference between discovering length 3 augmenting paths and length 5 augmenting paths, and the main challenge is discovering the middle edge of this augmenting path. Particularly, we do have these two, the second and the fourth edge. These red edges are given. This is the matching that we would like to augment. We have to discover these 3 edges, the 2 endpoint edges and the middle edge. And the challenge actually turns out to be the middle edge. And to further compare length 5 augmenting paths with length 3 augmenting paths, I'd like to quickly mention that the algorithm of Conrad, McNeas, and Matthew works even if the edges of the augmentation phase arrive in an adversarial order. So still, their algorithm does require the random arrival assumption because of the first guarantee that they can find the near half approximation early on. But once you have that, the augmentation phase works even if the edges arrive in an adversarial order. In a sharp contrast, however, if you want to construct length 5 augmenting paths, if you look at the paper of Goel, Kapralov, and Kano from 2012, it gives away a 2/3. This is a communication capacity lower bound. It gives away a 2/3 approximation early on for free. And yet, if the edges arrive in an adversarial order, it's provably impossible to augment this matching. What it says is that if we want to go beyond length 3 augmenting paths, and if we particularly want to be 2/3 approximation, even in the augmentation phase, we have to use the random arrival of the edges. And we do that in our algorithm. Particularly, how do we do that? We discover only length 5 augmenting paths where the middle edge arrives after the endpoint edges. Right? So these are the kind of augmenting paths that we find. And thanks to the random arrival of the edges, if you fix a length 5 augmenting paths, a length 5 augmenting path, there's a constant probability that the middle edge arrives after the 2 endpoints. And so there's still a relatively large fraction of length 5 augmenting paths that we can potentially discover. I won't have time to go through the details of the augmentation phase, but roughly speaking, up to the middle of the stream, we try to find endpoints of these augmenting paths via B matching, the green edges here. And then we spend the rest of the stream like discovering the middle edges, right? So if an edge arrives, you can plug it into a path of length 5 that you've stored up to this point of the stream, we just greedily apply this length 5 augmenting path. Right, so that's all I wanted to talk about. Just to conclude, we showed that the strictly better than 2/3 approximation can be obtained in the random order streaming setting using n log n space with high probability. And the main implication is that 2/3 is not the right answer for random order streaming setting. And the main open problem is, there are a few main open problems. One is, can we get this significantly better than 2/3 approximation? So our work goes slightly beyond 2/3 approximation. So what is the actual optimal approximation ratio? I should note that we make some partial progress on this problem in a recent work with Sepehr, which appeared in Random 2021. There we get around 0.7 approximation, not in the streaming setting, but in a robust communication complexity model, which is very related. Another open problem is, can we get actually the 1-epsilon approximation? And if not, ruling out a 1-epsilon approximation would be extremely interesting. And particularly, like the final open problem that I'd like to highlight is whether this greedy half approximation can be broken under adversarial arrivals. And I also want to point out that we, in the same paper, in this ICAL 21 paper, we give a lower bound as well. So it makes some partial progress on the second question. We show that if one wants to obtain a 1-epsilon approximation, the space needs to depend on epsilon, 1/epsilon exponential. So here's a statement of the guarantee that we get. And with that, I'm going to finish the talk. Thank you very much for listening.